Welcome back. I'm going to next describe the different things that can be done with differential equations. Nothing from here on in is testable. It's just for general interest. In addition to differential equations being used to model populations and model financial problems, we can also use differential equations for applications in the sciences. For example, differential equations can be used to model radioactive decay. A substance that is radioactive has some probability of decaying, of breaking up into smaller pieces, thus losing mass. Every component of that block of radioactive material, every nuclei, for example, has an equal probability of decaying at any instant. That means the more nuclei you have, the more decay events you're going to have. It scales with the mass. It scales with how much is there, just like population growth, except it's a population decay. So it has the same differential equation, dy by dt is equal to k times y. K is usually rewritten, rearranged, and expressed in terms of a half-life. And the mathematical expression for how much mass is there is given by a constant a, which is the initial mass, times 1/2 to the power of t over h, where h is a half-life. It's just a different way of rearranging that the exponential solution to that differential equation. A second thing we can model with differential equations in the sciences is mixing problems or fluid flow problems. I'm not going to go through it. You can read it if you want. The model there for saltwater mixing in a tank can be extended. You can do the detection of counterfeit currency using a model like this. Bottom left-hand side, Newton's law of cooling is another application. Newton's law of cooling says that if you take two objects that are different temperatures and put them next to each other, the rate of change of the temperature of one object is going to be proportional to the temperature difference between the objects, which is a really complicated way to say this. If you take a hot pizza and you want to cool it down, it's going to be faster if you put it outside when it's cold outside, or put it in a freezer. It's going to cool down more quickly. It's just a statement that the heat transfer between two bodies is faster if the temperature difference is great. Now there's other factors that come into play too. Different materials will have different heat transfer rates, but that's going to be embedded in this K value that's there. That K value is going to capture different materials properties. It's a constant that comes from experimental data. Where we would, if we were to use this as a test question, which we won't do, but in previous years it was done. Different problems can be given with pizzas coming out of an oven, cookies coming out of an oven, and asking if you want the temperature to be comfortable eating temperature, let's say 45 degrees Celsius, how long should you wait? So it comes out of the oven, and the cookie is going to be 85 degrees Celsius. And the kitchen, the room that it's in, might be 21 degrees Celsius. How long will it take to go from the oven temperature, or not the oven temperature, but the cookie temperature of 80 degrees Celsius down to 45 degrees or 40 degrees Celsius? You build a differential equation, solve the model, and you get 5.5 minutes. You get a reasonable amount of time that you have to wait before you bite into it. And then the last application that's on here is on smartphones, smart devices with touch screens. And how they work is they work with something called a capacitive resistance measurement. It takes the object that touches the screen, and it does a physics measurement of that object. It's quite interesting, but far outside the scope of this course, because to talk about it requires a discussion of circuits and interesting components inside circuits, which is definitely not something that you're expected to know. Thus, like all the other things on this slide, it's not tested. But I want to talk about one more thing that isn't tested, one more application. There's so many. Actually, I lied. There's so many. I want to talk about one more that's not even here. SIR models of diseases, models that are used by governments and by organizations to model the spread of diseases like the flu, like Ebola, COVID-19, different types of illnesses. those models, those compartmental models, are sets of coupled differential equations. So you have a rate of change of one quantity is related to another quantity, and they're related to each other. So one increases, the other one decreases. So there's like this feedback loop that goes on between the different components of the system. An example of that that's simpler than the SIR model, as it's called for epidemiology studies, is a model that was explored about 100 years ago, maybe 105 years ago, in World War II. And this model is a model of warfare between two sides. I'll call one of them the green side and one of them the purple side. And what it says is each of these, let's say, each of these circles represents a unit of soldiers, and they're going to fight each other. And as they fight each other, there's losses. There's members of each group are going to die, and the rate of change of the population of each group can be modeled as follows. So let's look at the green group. As they fight, the green group is not going to grow in size. It's going to shrink. They're going to lose people. People are going to die. So its rate of change is negative. It's a decreasing rate of change, a negative rate of change. And the magnitude of that negative rate of change is dependent on two quantities. Now remember, this is a model. It's dependent on other things, but as a simple approximation, we can say that there's going to be greater losses if our opposing forces are really good at inflicting damage. We're going to encapsulate their damage effectiveness with a parameter called little b. So if little b is a large value, then that means that the opposing forces can cause a lot of damage, can cause a lot of harm per unit time. Multiplied by capital P is the size of the population of the opposing force. Now the opposing force, they have their own differential equation. Their rate of change is also always going to be negative. They're going to be decreasing, and it's equal to negative C times G. C is the strength of the green force. How well can they inflict damage? G is the population of that green force. Then you have your initial condition, you have your initial population of green, your initial population of purple. This model is fairly difficult to solve analytically and is generally solved numerically. You can solve it with a computer, you'd solve it with, well, you can do a lot with pencil and paper, but now I would just explore it with a computer. It's more fun anyway. You explore a larger set of parameters. But the folks that were looking at these models came up with many insights. And again, this is a super simple model. Like there's nothing in here about the types of weapons that they're using. There's nothing in here about weather, about their ability for defensive capabilities, range, anything like that. Like it's all all those details are smoothed out. It's as simple as possible. And one of the things that came out of this, one of the findings, is about the importance of group size. That if you double the size of a group, you get more than double the effectiveness. You essentially get quadruple the effectiveness. And a striking way that this is seen in historical battles and battles today is in something called the bottlenecking effect. And if you click that link, it'll give you a YouTube video of a fellow that describes this bottlenecking effect and describes this square law very nicely. I invite you to look at that. And other things that this mathematical model describes for anyone in here that plays first-person shooters or real-time strategy games, it describes the reason why a lot of the good strategies in those games, why they're good, why they work. They are reflections of a mathematical structure, a structure that really rewards a large group versus a small group. If you go 200 fighting 10, it's vastly different than 10 fighting 20. It is more than 10 times of a difference. It's like, well, look at the video, you can calculate how much better it is. And to give an indication of what else is done with this, a simple model like this with small extensions is used to describe how conflict arises between animals, between chimpanzee groups, for example, or between fire ants. It's also used to describe certain features within human evolution, including human cultural evolution. There's a link at the bottom to an article. It's about 6 years old, but still fairly recent, that describes some of that. Anyway, this topic of differential equations is a window into mathematical modeling and a window into describing reality in a complicated and abstract but very powerful way. And it's one of the key things that's done with calculus. Take care, and that's the end of the course.